All right, I'm going to try and get her all into this last video. This is sort of the culmination of the topic. A little bit of a pun here. As unrealistic as it was to think about a bowling ball hanging out by the International Space Station, it was really unrealistic because when objects are that far from Earth, they're not stationary. They'd be moving as well, like orbiting the Earth or at least flying by the Earth. So to talk about their energy and only consider the gravitational field energy is inaccurate. Objects in outer space are going to be moving, which means they've got kinetic energy. Kinetic energy, luckily there's no new version for kinetic energy. Kinetic energy is the same that we saw in grade 11. It's 1/2 mv squared. Kinetic energy is always positive. Even if you do something weird with signs and say an object's going negative 20 meters per second, when you square the negative, it's going to flip it to a positive. So no matter how you slice it, we're going to get a positive kinetic energy. And from all the yabbering we've been doing for the last while, this gravitational field energy is always negative. When we think about something's total energy, it's going to have kinetic energy and it's going to have gravitational energy. When we add them up to get the total energy, we get this cool equation. This works for anything far from Earth that's moving. Its total energy is going to be the 1/2 mv squared plus the negative gmm over r. So it turns into 1/2 mv squared minus gmm over r. You take a pause and check this question out. Really, when we talked about the bowling ball by the International Space Station at 400 kilometers in height, when we did it before, we just did the negative gmm over r. We should take into account that it's moving as well and calculate the 1/2 mv squared and add those two numbers. I'm going to let you watch the video to check it. In Quadmester 4, and depending how we are doing for timing, sometimes we gloss over the satellite stuff, but the satellite stuff in the dark matter video that you watched, they show the math for this. There's a connection between the speed and the height of an object. Centripetal is always F net equals ma. So this is gmm over r squared equals mv squared over r. If we clean that up and we can play with it, there's a connection between the height and the r. We can do some work on that. You double check that a little bit. I just want to push on. This is my last little bit. Perfect. The last little bit. When something is flying in outer space, I'm going to break it down into two scenarios. The crockpot scenario and the Instant Pot scenario. The crockpot scenario is, if you've ever cooked in a crockpot, low and slow. If you've got an object that's close to Earth and it's moving slowly. If it's close to Earth, it'll have an EG that's a really huge negative number. And if it's moving slowly, it'll have an EK. The EK is positive, but it's moving slowly. The positive isn't going to be very large. If an object is low and slow, the negative of the EG overpowers the positive of the EK, and we get a total energy that's negative. If we think back to this line up here, maybe our kinetic energy is positive 1 million, but the gmm over r is negative 2 million. The positive 1 and the negative 2 end up with a total energy that's negative. What that means in astronomy terms is that that object is trapped. It's not going to fly away from Earth. It's going to be stuck in Earth's influence. This is kind of like you if you have a negative total at a poker game. Maybe you're down $100 and you got a $20 watch on. Even if you take together your positives and your negatives, you still owe money. You're not free to leave that poker game. Maybe you can walk around the room as you collect your thoughts, but you're not allowed to leave. An object that has a total negative energy, maybe it'll orbit Earth, maybe it'll sort of loop around, but it's never going to leave Earth's influence. As opposed to our Instant Pot scenario, if an object is high and moving fast. If it's moving fast, we'll do this first, that means it's got an EK. EKs are always positive, and if it's moving fast, the EK is going to be a really large positive number. If it's really high, that means that the EG number, which is always negative, maybe it isn't very big. In a case like this Instant Pot high and fast scenario, the negative is overpowered by the positive EK. So it's so fast that it's got enough kinetic energy to overpower the negative. Its total energy is positive. If we do the math and find that the total energy on an object is positive, that object is not trapped. Its path may bend because it's close to Earth, but it will leave and keep flying into deep, deep outer space. This is like you at the poker game and you're doing so well, you're positive money, you can get up and walk away whenever you want. This is things like maybe you read in the news, you see NASA notices an asteroid approaching Earth. They would do the math on it and compare the kinetic energy of that asteroid to its gravitational field energy of the asteroid. As long as that number comes up positive, we know that that asteroid isn't going to, unless it's on like a direct route and going to just fly into us. If we've got an asteroid zooming by kind of like this, if it's going really, really, really fast, then it's not going to stay trapped close to Earth. This is supposed to be Earth. It may bend, but it'll fly away and go to deep, deep outer space, and we don't have to worry about it. That's it. I've got some examples for you to practice. There's a worksheet there for you to work on too. It's a little bit weird because the energy is negative. The proof is weird because it involves calculus, but hopefully the concepts start to stick. If the total energy of an object is negative, that means the object's trapped. If the total energy of the object is positive, it's not trapped. It may bend, but that object will eventually leave Earth's, or whatever the big M is, influence. That's where I'm going to shut her down on the video. Check out this example. Check out the worksheet. There is a check-in problem. And I found this really cool. It's relatively recent. The Japanese Aerospace Exploration Agency did some really, really cool work. They would have to use some crazy math to do it, but all based on the math, the topic that we did today. So take a look at that if you're bored too. Good luck. It's my favorite topic. I hope it made sense. As always, if you have any questions, email and we'll sort it out together.